So what we have learned right now, we have learned all about basically first we have started our journey from Schrödinger wave equation for hydrogen atom. We have just to get lot of information from there, mainly principal quantum number and the transition between these particular principal quantum number. But once we go to the very microscopic level of analysis, then obviously we have just bring more information into calculation in term of perturbation. So we have learned the fine structure part. Obviously, I have discussed the relativistic part and the spin orbit part. And yes, there is one more part is that is what Darwin part is also. These three will complete it as a fine structure. And these are due to the internal, either due to internal motion of a electron or a internal interaction between electron and proton, isn't it? This is the internal part of atom. Whatever with the field, whatever with the splitting are due to the internal field of atom, isn't it? We assume that electron will feel the magnetic field due to relative motion of proton, and due to this relative motion of proton, there are internal magnetic field in the atom, and due to that we have learned all about spin orbit coupling. So these all things will be combined together, and they are identified as basically they are just identified as mainly your fine structure. Just give me 1 minute. Okay, so we have just seen this particular thing due to internal interaction between electron and the magnetic field develop due to the motion of proton, and we have that magnetic moment of electron will be going to interact with this particular field, and we have that S dot L as our spin orbit coupling. Now what we are going to do, we will just put our hydrogen atom, or in any atom, you will learn it later when you have a 2-particle system and 3-particle system. But today we are just going to discuss when we will put the hydrogen atom into external magnetic field, then what is going to happen. So here we are just talking about external magnetic field. So this is one of the basic difference between a spin orbit and Zeeman effect. So this is all about external magnetic field. So if we are putting our hydrogen atom into external magnetic field, there are further splitting. And that splitting can be understood by Zeeman effect. And you will be surprised that the experiment of Zeeman effect have been done early before the quantum mechanics. So once quantum mechanics come into picture, it mathematically explain this particular experiment. So this is a very interesting thing. So first we will discuss the normal Zeeman effect. In an ideal case, what is going to happen, and then we will discuss the anomalous and Paschen-Back Zeeman effect for different conditions. Okay, so the normal Zeeman effect will give you idea what is going to happen. So obviously, what we have electron, and this electron is just going to interact with some external magnetic field, let's say B. And we deliberately saying that B is in Z cap direction. I will also discuss what will happen when B will be in any orbit direction. We can solve it easily because we have done quantum mechanics in a very nice manner. And here for the normal Zeeman effect, we are just ignoring the spin of a electron. So there is only one thing, that is what your orbital angular momentum is there. So yes, if any charged particle is rotating in some circular orbit, there is orbital magnetic moment, and due to that there is some interaction, and this interaction can be identified as Z Zeeman, and this is nothing but minus B, and it is that external magnetic field. You are putting magnetic field from the outside of this particular electron from any, it means you can just put this magnetic field. So this is nothing but this will be given by mu, and here we are talking only mu L dot B external. So this is your energy due to interaction of electron due to this orbital motion with external magnetic field. And we all know that hence electron has negative charge. So this all thing will be positively defined, negative will positively. You can write mu L as a E upon 2m, and there will be L vector, and you can take negative because charge is negative. So this is your angular momentum vector. So this will be positive, and you can write E 2m, and here you have L dot B external. L dot B external. Now, here in ideal situation, what we are saying? We are just saying B is in the Z cap direction. So what is direction of B? That is in Z cap direction. And we have E upon 2m. And now if B is in only Z cap direction, then only Z component of L is going to couple with this. So we have LZ B external. And obviously, what is our good quantum number here? The quantum number NLM is the sufficient to discuss this H normal Zeeman effect, because LZ will operate on this one. What you will get? You can just NL and ML I can use, and this value is equal to, if we are just taking the average value or first order perturbation we are just going to discuss, then this will be H Zeeman is nothing but we have E upon 2m, and this value is equal to ML H cut, and this is what? B external. And what will be this value? This value is equal to E H cut, and this is mass of the electron, and you have a quantum number ML and B external, and this is very famous quantity that is known as what? Bohr magneton, isn't it? So this is basically known as what? Bohr magneton. So this energy splitting due to Zeeman is basically mu B ML into B external, and this is nothing but the magnitude of B external. And now you can see this splitting is proportional to ML, and which is linear to ML. So this will be equally spaced, isn't it? So ML, delta ML is what? Plus minus 1. Are you getting my point? So yes, you can have, and this is linear in ML. This gene ZE energy due to interaction of your atom to your external magnetic field is something like this. Now my question is that normal Zeeman effect is very trivial case. So this is not a very complicated case. The normal Zeeman effect, suppose I put my magnetic field in any arbitrary direction, then what you will do? How you will go for this? Suppose I put magnetic field in any arbitrary direction, not in Z direction, then what will happen?
Sir, n cap को r cos theta sin theta के term में लिख.
Exactly. What you will do? We can just go for E upon 2m, and we have L dot B, isn't it? So what you will do? You will just divide with the magnitude of B, and you will multiply with the magnitude of B, isn't it? And what is this particular thing? B upon mod B?
N cap.
E upon 2m, and that value is L dot n cap into magnitude of B vector. Yes. And what is L dot n cap? L dot n cap has exactly same eigenstate, which will be equivalent to what? LZ. ऐसा हम लोगों ने कर रखा है ना क्वांटम मैकेनिक्स में?
Yes.
है ना? So L dot n cap has exactly same eigenvalue. So L dot n cap has same eigenvalue as LZ. So what will happen? So this value is equal to E upon 2m, and again it will become ml h cut and magnitude of mod B, and now you can say this value is equal to E h cut upon 2m, or you can just write Bohr magneton mu B ml into magnitude of this particular thing. So suppose I am putting my magnetic field such as, B naught I cap plus j cap, then what will be answer? क्या होगा अगर इस डायरेक्शन में मैंने मैग्नेटिक फील्ड पुट किया तो क्या होगा? Just give me answer. What will be mod B now? Mod B क्या होगा?
Sir, √2.
√2 B naught, isn't it? So here
Yes,
mod B is equal to √2 B naught, and you can just put it in this,
√2
है ना? E Zeeman one level is equal to what? √2 mu B into B naught, isn't it? This
Yes.
and ml is also there, and root and ml is also there, isn't it? So this will be your normal Zeeman effect. But obviously, normal Zeeman effect is a very ideal case. We all know that there are internal rotation of a electron, and this is identified as what? Spin. So spin will also come into picture, and when spin will come into picture, L will come into picture, then obviously the thing is just going to change. So let's go for actually what is Zeeman effect, known as when we are just using L as well as S in our calculation. ठीक है यहाँ तक? But idea develop हो गया है ना कि idea क्या है? Okay.
Yes, sir.
So let's try to go for actually mainly we have to mainly there are three type of Zeeman effect: weak Zeeman effect, strong Zeeman effect, which is popularly known as what? Paschen-Back, and most important thing is that one is there is intermediate Zeeman effect, but intermediate Zeeman effect is not in our course more or less. This is little bit tougher part. Now, why we are giving this as a weak Zeeman effect, strong Zeeman effect, and intermediate Zeeman effect? So where is the reference? Something is weak and something is strong, in which from which relative argument you are just trying to say? क्या बता सकते हो क्या रिलेटिव आर्गुमेंट है कि हम वीक किसे कहें, स्ट्रॉन्ग किसे कहें? भाई आप पढ़ते हो ना वीक जीमेन इफेक्ट, जिसे वेरी फेमसली क्या कहते हैं? एनोमलस जीमेन इफेक्ट, इजंट इट? वीक जीमेन इफेक्ट, जीमेन इफेक्ट, जिसे आप क्या कहते हो? समटाइम यू विल टेल व्हाट? एनोमलस. Anomalous Zeeman effect. Okay, what is weak Zeeman effect? Anomalous.
सर मैग्नेटिक फील्ड का स्ट्रेंथ के ऊपर
हाँ, लेकिन किसके रेस्पेक्ट में वीक या किसके रेस्पेक्ट में स्ट्रॉन्ग? मैं ऐसे थोड़ी, वीक या स्ट्रॉन्ग कोई एब्सोल्यूट टर्म थोड़ी है. This is a very interesting. What is your weak Zeeman effect? Why? What is meaning of weak magnetic field? किसके कंपैरिजन में weak magnetic field है? So now you can think. It's a very, so we have two type of magnetic field. One magnetic field is internal magnetic field. Due to spin orbit coupling is going to happen. Are you getting my point?
Yes, sir.
अभी तक हमारे पास क्या था? Our Hamiltonian is H naught. H naught is actual Hamiltonian given by Schrödinger, and here we have just add on HR relativistic, and then you add on LS coupling, plus you have add on some Darwin term also. I think Mukadder sir have told you this particular Darwin term. है ना? And this combined way, you are saying this thing is H naught plus H fine structure. है ना? These are things. And in the fine structure, there are internal magnetic field. Yes or no?
Yes, sir.
This is internal magnetic field. So B internal. Now, if your B external is less than B internal, are you getting my point? If B external is less than B internal, then you are using the weak Zeeman effect, and which is actually identified as anomalous Zeeman effect. Are you getting my point?
Yes, sir.
So why we are
Yes,
giving it the weak name? Okay. Now what is going to happen? Suppose this is my, and now I can assume this is the magnetic field in Z direction. Okay. So there is magnetic field in Z direction. So there is L vector, there is S vector, and this is your J vector. Yes. What will happen? L vector and J S vector will precise about J vector, something like this. It can precise something like this. It can precise something like this. Okay. Something like this about J vector. है ना? So this can be precise L and S. You can just assume that L and S can precise about J vector. But when you will give the external magnetic field, whole J vector is going to precise about your magnetic field. This is your B external. The whole J vector is going to precise about magnetic field. And there is the coupling will come into picture. And now due to up to this level, please mind it, this is very interesting. Hence, we have this all initial information. We don't want to lose our information here. So our good quantum number is mainly N, L, J and MJ. Are you getting my point? क्योंकि फाइन स्ट्रक्चर के अंदर क्या आता है? N और J? Yes. Are you getting my point or not? N and J will come into picture, and you will see that L square is just going to commute with this thing. So if L square is going to commute with this thing, then L will be also a good quantum number. But S is not going to commute with this thing. So obviously this is not a good quantum number. Now look at how the bigger problem will come into picture. So now what is going to happen? Again, we have external magnetic field, and I can assume this external magnetic field in Z direction. There is not any problem. So if this external magnetic field is in Z direction, again we have H Zeeman. H Zeeman is identified as mu L plus mu S dot B external, and negative sign is also there due to this particular fact of how magnetic moment and this particular magnetic field are going to, and this is what mu L. Okay. So now, hence this is electron, and this electron have negative charge. So this value is equal to E upon 2m L plus G E upon 2m S. Sorry, this will be S, and this will be into B external. And what is the G value? Obviously, the G value is identified as 2 for your basically a spin half particle or electron. So now the whole thing we can take E upon 2m common. The thing will be L plus 2s into B external. Now I can write this 2s as L plus S. sorry, 2s as s plus s, then this whole thing can be written as E upon 2m j plus s. Are you getting my point? ऐसा ही होगा ना?
Yes.
Now, look at your state. What is your state? Your state is n, l, j and mj. We can easily get the average value of j on this particular state. But it is very difficult to get the average value of s on this particular state. Because actually we have to calculate E-Zeeman 1 is nothing but average value of H-Zeeman on the state NLJMJ. And you know that this fine structure will come into with N and J, isn't it? So this is very interesting that we know what is the value of J, expectation value of J. This is vector quantity, don't worry. This is vector quantity, but we can get the average value of J here. But the toughest thing is that how you will get the average value of S on this particular state. Are you getting my point? The average value of S on the state N, J, L and Mj, S is very tough. N, J, L and Mj. This is very tough. So now here we are just going to make a trick. And what is this trick? This trick is very interesting. If you have any vector A and you just want to project this vector in direction of n cap. So what will be that projection of A in direction of n cap? A dot n cap, isn't it? So this is a very beautiful lemma known as projection lemma. So we will just use this trick. Now suppose you want to project A in a direction of B, then what will happen? A dot B, इसको भी mod B से divide कर देंगे तो क्या हो जाएगा ये? Unit vector. And again you have B by mod B, then you have exactly same thing. So what we are going to do, we will just trying to project my S vector. We just trying to project my S vector in a direction of J. Are you getting my point? So we actually क्या हो रहा है? S is just precise over J और J is precise over B. तो S का वही component काम करेगा जो J की direction में होगा, isn't it? So we are taking that those component of J which is in the direction of, those component of S which is in the direction of J. So here we will just go and we can just find this particular value with this particular lemma, and this lemma is basically identified as S dot J, isn't it? B की A के जगह पर क्या हो गया? S. किसका प्रोजेक्शन लेना है? S का. किस डायरेक्शन में? J के डायरेक्शन में. Obviously I have to make it unit vector, that is J, and we have to just go for J by mod J. Are you getting my point? So what will happen? This S vector can be written as S dot J by mod J square and in a direction of J, isn't it?
Yes.
है ना? And we can easily find S dot J. S dot J की वैल्यू हम easily निकाल सकते हैं. Yes?
Yes.
And this is a scalar quantity, so there is not any problem. But this is vector quantity, and now everything is written in term of J. लिख सकते हैं ना? So let's try to write the. हाँ बताओ.
सर इसमें इसको जो J इक्वल टू L प्लस एस है, इसको उस टर्म में नहीं लिख सकते हैं, मतलब
J is equal to L plus S.
J इक्वल टू L प्लस एस, तो S इज इक्वल टू J माइनस L. तो
अरे ये वेक्टर है ना, वेक्टर को लिखना है हमें एक्चुअली. आप चाह क्या रहे हो? तो फिर उसके लिए L को निकालना पड़ेगा. आर यू गेटिंग माई पॉइंट? एल का इस तरह से लिखना पड़ेगा, बात तो बराबर ही होगा। बेसिकली आप यहां देखो, इस बी के डायरेक्शन बी के अबाउट कौन प्रिसाइज कर रहा है, जे प्रिसाइज कर रहा है। ओके, तो या तो आप
यस
एस को अगर यहां इंक्लूड करते हो तो एस को जे के डायरेक्शन में लेकर आना पड़ेगा, अगर एल को रखते हो तो एल को जे के डायरेक्शन में लेकर आना पड़ेगा,
ओके ओके
है ना, बात तो बराबर ही है। ठीक है,
ठीक है
ओके। Now the whole thing can be written as this Zeeman effect. So E Zeeman is given by 1 plus S dot J by J square, and here is basically J dot B, isn't it? And you have E upon 2m, and we have to take the average value of this also. ठीक है, and obviously B is in which direction?
जेड
Z cap direction. So B is in Z cap direction. So only J, the Z component of B will going to couple with this. So you have E H cat upon 2m, and you have Mj. There is B as a magnitude, and you have 1 plus S dot J by mod J square, and this is very famous, known as Landé factor. Are you getting my point? अभी देखते हैं क्या होता है. So this is just a number. This is a scalar. This is a scalar. So this will be just a number, isn't it? So this whole
यस
thing is mu b is Bohr magneton. G, this is your Landé factor. Mj into magnitude of B. Yes. And now what is the value of G? This Landé factor can be defined as basically 1 plus what is S dot J? What is S dot J? कैसे लिखोगे S dot J को? So you will just write J into J plus 1 plus S into S plus 1 minus L into L plus 1. H cut square is there, but J into J plus 1. सही है ना? Yes. And what will be S into S plus 1? 3 by 4 H cut square. Clear है ये? So this is nothing but 3 by 4 H cut square. So this will be 1 plus J into J plus 1 minus L into L plus 1 plus 3 by 4 H cut square is cancelled by J into J plus 1. And this is very famous Landé factor. Yes? So this is basically correction due to Zeeman effect. Okay, because this is your weak magnetic field, Zeeman effect, and that will be mu b, g, mj, and b. So for the given value of j, you have further splitting, है ना? Given value of j, you have what? Further splitting. If your j is equal to 3 by 2, then what is going to happen? Then you have 4 level of splitting, plus 3 by 2, plus half, minus half, and minus 3 by 2. So you have this sort of your E Zeeman. Okay. So this is your very famous anomalous Zeeman effect. Clear है ये? So we use just quantum mechanics, nothing else. आपको इसका जो फिजिक्स है एक्चुअल Zeeman effect का, व्हाट इज ट्रांजिशन, किस तरह से पाई है, सिग्मा है, वो सारा चीज आपको मुकद्दर से डिस्कस करेंगे. बट आई एम जस्ट यूजिंग द क्वांटम मैकेनिक्स. ओके. एंड अगेन फिर से मैं यहां पर क्वेश्चन पुट कर सकता हूं, इफ बी इज इन एनी ऑर्बिट डायरेक्शन, देन अगेन यू विल मेक व्हाट? जे एज अ यूनिट वेक्टर, है ना? बी को फिर से यूनिट वेक्टर में कन्वर्ट कर देंगे. ठीक है?
यस
yes or no? But in general we are thinking that J is basically magnetic field is in Z cap direction. So हम लोग उसे लेकर के काम कर सकते हैं. ठीक है? So let's
Yes.
go for a anomalous Zeeman effect. What is going to, sorry, let's go for what? strong Zeeman effect, and this is very interesting. Now look at here, और इसको थोड़ा बहुत ही मजेदार ढंग से आपको समझना होगा. This is your strong magnetic field. Here is what? Strong. What is meaning of a strong magnetic field? B external is very, very greater than B internal. Okay. So now, अब जो यहां पर आपके लिए बात हो रही है वो चीजें आपको आसान कर दे रही है. What will happen when you will give the enough strong magnetic field? Then what will happen? The LS coupling is going to break down. And what will happen? L will be precise about magnetic field independently. S will be precise about magnetic field independently. So there is not any role of J. Are you getting my point? So what will happen? Now the good thing is that you have a Hamiltonian, and the Hamiltonian is your Schrödinger Hamiltonian, which is H naught. And now you can have Zeeman Hamiltonian. Why Zeeman Hamiltonian? Because B external is very, very greater than B internal. So here perturbation term is your LS coupling. That is very weak, isn't it? Are you getting my point?
Yes.
Because जब आपका L और S precisely B के about आपको precise करने लगेगा L और S, then there is not any role of J quantum number. Then L and S is a good quantum number, isn't it? So what will be your H Zeeman? And this will be diagonalized matrix. Don't worry, H Zeeman. And here is perturbation, and the perturbation is basically L and S. The coupling term is treated as a perturbation, and these two term is treated as a original Hamiltonian. जैसे weak Zeeman effect में हमने क्या किया था? Fine structure के basis में सारा चीज लिखा था, है ना? We have further perturbation term with the H original plus your H fine structure. So now what will be this H naught is there, and this value is equal to E upon 2m, and there is Lz plus 2 times Sz, isn't it? और यहां पर जो quantum number होंगे, that is what quantum number? N, L, because there is not any coupling. N, L, Ml and Ms. These are the good quantum number. So you can easily find what will be if when you are just going to operate on N, L, Ml, S and Ms. अगर आप इसके ऊपर ऑपरेट करते, you can easily find this Lz is what? Diagonalize. This Sz is what? Diagonalize. This H naught is what? Diagonalize. So this is your diagonalized term, and this is your perturbed term. Are you getting my point?
Yes, sir.
है ना? So this is your Zeeman part, and now here you have basically Lx, Sx plus Ly, Sy plus Lz, Sz. Now the average value of Lx, Sx on this state is 0. Average value of Ly, Sy on this state is 0. Only that the thing is going to survive is Lz and Sz. So what will happen? You have H naught plus E upon H cut upon 2m. And what you have? You have Ml plus 2 times Ms, na? 2 times Ms. And now you have this term is average value is 0, and you can separately find that Lz as well as Sz. And what is this particular? This is your Zeeman effect, and this is basically known as what? Paschen-Back, and this is LZ and SZ. So, and this is your perturbation term. Okay, यहां पर J का कोई रोल नहीं है. Are you getting my point?
यस सर.
है ना? तो ये
सर
तो
इतना इनफ मैग्नेटिक फील्ड है कि कोई कपलिंग भी नहीं होगा,
कोई कपलिंग नहीं हो पा रहा है. एग्जैक्टली, कोई कपलिंग नहीं हो पा रहा है. कपलिंग का क्या बात है? अब तो यही ओरिजिनल हैमिल्टोनियन आ गया ना. आर यू गेटिंग माय पॉइंट? पिछले बार क्या ओरिजिनल हैमिल्टोनियन था? पिछले बार हमारा ओरिजिनल हैमिल्टोनियन था एच नॉट प्लस एच एफ एस. ये हमारा ओरिजिनल हैमिल्टोनियन था और यहां पर ये वीक था. आर यू गेटिंग माय पॉइंट? अब ये मैग्नेटिक फील्ड के आ जाने के कारण, मैग्नेटिक फील्ड इज ऑल्सो देयर इन बी डायरेक्शन, सो बी इज ऑल्सो देयर. तो अब स्ट्रॉन्ग मैग्नेटिक फील्ड होने के कारण, और स्ट्रॉन्ग मैग्नेटिक फील्ड किसके रेस्पेक्ट में कम है? बी इंटरनल के रेस्पेक्ट में कम है. देन ऑब्वियसली जे इज नॉट देयर. आर गेटिंग माय पॉइंट? है ना? और वो कपलिंग भी इफेक्टिवली ब्रेक हो जा रहा है. सो यू हैव दिस पर्टिकुलर पार्ट, एंड दिस इज वेरी फेमस, नोन एज व्हाट? Paschen-Back effect. So EH by 2m is mu b, and you have ml plus 2 times ms into magnitude of b, and this will be correction due to H Zeeman in strong magnetic field. लेकिन टोटल हैमिल्टोनियन के बारे में बात करोगे, व्हाट इज दिस पर्टिकुलर थिंग नाउ? -13.6 by n square. Okay, and you can find ml and ms. And what is this LZ? What is this LZ? ml. And what is this SZ? That is ms. अगर तुम complete answer निकालोगे, then this will be your answer. So now up to Zeeman effect, you have -13.6 by n square plus you have mu b into b into ml plus 2 times ms plus you have ml into ms h cut square. H cut square will be there. Are you getting my point? So this is your complete information, but Zeeman part is, this is the basically Zeeman part, which is very popularly known as what? Paschen-Back effect. Now, the toughest thing is that when your B external is comparable to your B internal. Are you getting my point? दोनों एक दूसरे के comparable है, and then it will create a havoc, which is basically known as intermediate Zeeman effect, which is not a scope of this course. ठीक है? इस कोर्स का स्कोप में नहीं है. So now इसके बाद की जो बातें हैं, जो आप सिलेक्शन रूल, ट्रांजिशन, ये सारा चीज है, वो जो आप देखने की कोशिश करोगे, that will be into the next class given by what? मुकद्दर सर. ठीक है?
Yes, sir.
Okay, so this is just a quantum mechanics. This is just a quantum mechanics we are doing. Okay, but इससे आपको पता चलेगा कि आप एक्चुअली कर क्या रहे हो. What is going to happen? Which type of mathematics is there? Yes, चूंकि मैंने क्वांटम मैकेनिक्स पढ़ाया है, तो उस अनुसार मैं चीजों को लेकर के जा रहा हूं. ओके, and Mukadder sir will just use this statement, and then after then he will give you selection rule and all the transition and और सारी चीजें करेंगे. So one particle के बाद वो फिर 2 particle 3 particle में इसी तरह से चीजें कोरिलेट होती जाएगी. ठीक है? So this is from my side of. इसमें आपके प्रॉब्लम डायरेक्ट क्वांटम मैकेनिक्स में भी आ सकते हैं इन अ परटर्वेशन. आर यू गेटिंग माय पॉइंट? सो आपको अपना ब्रेन ओपन करके रखना है. ओके, चलो, थैंक यू.
सर ये जो रिलेटिविस्टिक और डार्विन टर्म वो भी इंक्लूडेड होगा इसके साथ?
किसमें?
ये जो
ओके, यस, दैट विल बी देयर. रिलेटिविस्टिक टर्म इज देयर. ठीक है, मैं उसे मिस कर गया. सो रिलेटिविस्टिक टर्म इज देयर, बट ये वाला टर्म पर इफेक्ट पड़ जाएगा, है ना?
यस.
ठीक है, इसके ऊपर इफेक्ट पड़ जाएगा. रिलेटिविस्टिक टर्म में क्या आता है? एल ही तो आता है. आर यू गेटिंग माय पॉइंट? In a relativistic term, L will come into picture. So L is there. There is not any problem. है ना? J किसके कारण आता है? J will come due to this one. Yes?
Yes.
है ना? तो ये ब्रेक हो गया, तो ये भी L के टर्म में और S के टर्म में आप लिख सकते हो. ठीक है? And this thing is given in a very nice way in a Griffith. So you can just go and learn in a Griffith. Okay? बहुत ही अच्छा सा दिया हुआ है. Actually, I am following that thing. ठीक है? So मोर और लेस आपको बहुत अच्छे से समझ में आएगा एक एक चीज. ओके,
यस सर।
Okay. Thank you.
थैंक यू सर।
Thank you.